备好了吗？是不是那个就是电脑都有检查过，然后甚至第二台备用的电脑都检查过了？如果可以的话，那我们现在开始可以吗 ？Okay. So if there is no objection, we are going to start our fight today. Allow me to make a brief introduction. Please, my name is Charles Jiahui Yang from Hongjia University, and from there, could you introduce yourself from Professor Yu here?
I'm Xun Zhong from National Kaohsiung University.
Chen Shuai from Sida.
Han Xiaoyin from Hongjia.
Bao Jianhua from Zhongzhen University.
Okay. So, if there is no objection, please let's choose the problem. Okay. So.
We challenge problem number 7, or 10.
So the reporter.
We would like to accept.
Okay. Well, in that case, please reporter and opponent and the reviewer, please write down the name on the board and write down the accepted problems. And please write it nicely, because the juror here will have to copy your names on the grading sheet. So the accepted problem is that number, which one? Number 7. Please write it down over there. So if there's no other problem, the reporter will have say roughly 4 minutes to be prepared. Go ahead. You may make your case if you like.
Hello everyone, I'm Isaac Zhang from Team Medical from CGI School, and today we are going to present the problem 7, ruler can. The problem statement is shooters are tightly held against each other. A round projectile, especially like a plastic bottle can or a ball, is inserted between them close to one of their ends, where actual force is exerted on the surface of the rulers. The projectile is ejected at high speed. Investigate the effect and the parameters that affect the ejection speed. Our key question is, under what conditions can the projectile be ejected? And the second one is, what makes the projectile effect faster? This is our order. We are moving on. We are going to present the observation, the theory, then the experiment, and the conclusion. This is observation. Wait. If we can, in all observation, okay. This is our theory for magnetic field. The parameters is like that. The F means the force we attracted, and L means the length of the ruler. Z means the end, from the end to the first point, first attach point, and distance. And R means the radius of the ball. We define alpha equals to Z divided by L. From L beam theory, we know that we consider the torque equals to this, and the moment, the area moment equals to this, and we know the torque equals to the normal for times the length. And we have to estimate the angle of tubular and curvature of this one and this one. And we consider the moment of the ball. But we define T. Delta T is the constant. According to previous derivation, we know that V should obey the equation, and the equation should obey the condition of ejection. And this is our experiment. This is our setup. We use a board going to attach. It is ejected, and this is setup. We use the machine to and spring to control the ruler and control the force and the ruler, and we use ball as a projectile. And we do the experiment of friction ratio. We place the ball on the ruler and gradually increase the slope until the ball starts to slip. Then we use the equation to calculate the coefficient of friction between the ball and ruler. When the theta is equals to this, the ball starts to slip, which is almost the same as the condition we mentioned previously. and the ejected velocity is like that. We notice that when alpha equals to 0.5, the velocity goes the minimum for the equation of the area moment, and have the minimum in this place, and the area moment affects the ejective velocity. And this is our conclusion. The relation between the moment arm and the ejective speed should be that. And the ejection condition is that. Thank you.
Okay, so I guess the next one here would be the opponent to make your case.
Okay, I'm the reporter from Team Web. So my first question is that why do you use a polynomial fit?
So sorry, what?
Why did you use a polynomial fit?
Polynomial fit. Because according to our theory, the moment of the area should be that.
Okay, so how does this come out? Because I don't know.
Can you use the blackboard?
Later.
Okay.
Do you consider in your friction testing experiment? Do you consider the ball is rotating?
No.
It's just like that.
But we use two.
Okay. Next question. Can I ask what is delta t?
Delta t means the time from it is stable to it is ejected. We consider it as a constant.
Okay. Next question. So can you again say what is L and what is R?
L is the length of the ruler and R is the radius of the ball.
Okay. So you approximate the angle. Like it's a very small angle. You use that term?
Yes.
Okay. So next question. So in your theory, you consider the beam as a cantilever beam?
We consider what?
Do you consider the beam as a cantilever beam?
What? How do you define cantilever? I don't know that word.
Okay. Next question. So do you consider the?
Oh, okay. Now we have to switch to the other. So now the reviewer. So you no sorry. We have 40 minutes to make the formal discussion between reporter and opponent.
We should have opponent.
Oh, sorry.
3 minutes.
Yeah, so you have to give them 3 minutes. So the reporter, please. The opponent, please.
Good afternoon, honorable judges and fellow opponents. I'm the opponent, fellow reporters and viewers. I'm the opponent from Team TYPT. The problem I'm going to oppose today is ruler cannon. So let me restate the problem statement. Two rulers, as in the experiment setup, are tightly held against each other in a fixed side. Their round projectile, like they use a marble, is inserted between the close to their ends. So an extra force is inserted on the surface. They use spring. So the projectile is ejected at a high speed, and they measure. So they investigated this effect under which condition and how to determine the speed. Okay, so when force is applied to the ruler, the ball ejects. In the theory, they mainly use a Euler-Bernoulli beam theory, which I might need to ask them later. And also, they use the friction formula to test the friction coefficient of the marble. Also, they use a polynomial fit based on the Euler-Bernoulli beam theory. And according to the experimental setup, they use hands to push the strings and apply force on the ruler. They also test the friction coefficient. Now, let's talk about their advantages and disadvantages. First, they have thorough explanation of the theory. Also, they consider the influence, the ruler, like the deflection and the friction. However, there are some cons. For example, there are not clear observation videos. Also, some labels are undefined. Like, for example, the symbols might need to be clearer. Also, they can explain more about the experimental setup, and using a machine might be more precise. Now, this is the important point. The discussion that I would like to perform with the reporter are the following. First, about the phenomenon. No, not yet. I would like to ask that, have you ever considered the rotation of the ball when you're testing the friction coefficient? Because when the ball rolls down the slope, it is not a slide, and I don't think the coefficient is really correct. Also, I want to ask that what forces cause the ball to eject? Also, do you have a clear definition of your release point? For example, in the problem statement, they say it's the end point, but how long to the end? Okay, about theory. We want to again ask about why do you use a polynomial fit and whether it is appropriate for this problem. And also, what kind of beam model did they use? Because the formula somehow just popped out of nowhere. Okay, and why did the force equals to this thing? Because we think that the force changes over time, so this needs to be integrated, well, not written by only a multiplication. Also, about other discussion points, I would like to give some advices to substitute their experimental setup using hand. So now I would like to invite the reporter up to the stage for the discussion. So, can I see your preliminary experiment where you tested the friction coefficient?
Yeah.
Oh, thanks. Yeah, in this experiment, you tested the friction coefficient between the marble and the ruler, right?
Yeah.
So I understand it is very difficult to test the friction between a ball and a ruler, but do you think this is the coefficient is really correct?
Correct?
Yeah. Do you think it is?
It is.
I don't think so. And I'm going to say my reasons. This ball here is rolling, and this only fits with the, can I use the blackboard? This model, like mu equals to tangent phi only fits when this is a slope and there is a box sliding downwards. And the model, in reality, this is a ball, and so you cannot do it like that.
Yeah. So, sorry for I didn't explain it well. So we use a little box. We use a little box. The limit is not rolled.
Oh.
And the box, and we still consider the box as eject.
Okay, so you make sure that the box and the ball are on the same plane, like they're both touching.
They are all on the ruler.
So how do you calculate this ball's coefficient? Because you have both the box and so you cancel it. Oh, I think this is a very good method.
So I use something to hold it in not rolled.
Oh, okay.
Sorry for not explaining well.
So maybe you should show it in the diagram, because if I just see this coefficient, I would say that it is wrong. You need to show a real experimental setup. And about the next question, I want to ask, what forces cause the ball to eject? What forces? When the ball ejects, what forces act on the ball?
Still use the blackboard. This is a shoe roller, and there is a ball, the mono force, and the friction.
Yeah.
Sure.
So, you say that these two forces act on the ball, right?
The friction can equals this one.
Yeah. And here, you use a spring here.
Yeah.
It is not in the middle. I know that. And you exert a force from here. So do you think this force has the same direction with this end? Because this is a bending ruler.
Sorry, can you repeat your question?
You use a spring, and it is in this direction, right?
Yeah.
But your ruler is like this. So when you push it, don't you think you should put the spring like this?
You mean this? We push it in here,
Yeah.
but you think we should put it in this direction?
No, I don't suggest that, because I don't think this is a good idea. But in your calculation, do you consider the force in this direction the same as this one? Because if you want to measure the torque, you need to know that the angle here and here might not be the same.
But the angle is very small.
Is it really small?
Theta is very small, so the force of the spring and the ball is the part. So for the ball is really small. If you put like this way, you attach force like this or like this, or the same.
So you think that it can be negligible?
Negative, yeah.
Okay, I think I can solve that. So the next question is, how do you define your endpoint? Do you put the ball in the same direction, same position?
You mean the attach point?
Yes. Is it the total endpoint a little bit more here or here? Because that affects how open your angle is here.
We put it in the same place like that.
How do you define the same place?
You can just use the measurement and measure the length and define the place and put the ball in this place.
So you make sure that the ball is always in the same place.
Yeah.
So do you think that when the ball is ejected, are there moving, because this is static friction, right?
Yeah.
Are there like motion friction? Do you consider that, or does it just instantly pop out of the ruler? do you consider that there is still an acceleration that goes to here? Do you consider that?
We approximate that. What do you mean?
So if your ball is like this,
Yeah.
and when the ball ejects,
Yeah.
the angle gets smaller, right?
Yes.
So when the angle gets smaller, the ball shifts outward like this. Do you consider that even after the threshold of static friction, the ball still remains on the ruler?
Well, as I said previously, the theta, the angle is too small.
I know, and like these theta should be the same. But do you consider that the ball is still on the ruler after it starts to slide? Or does it just eject? What's your opinion?
Oh, wait.
Just does the ball slide on the ruler?
The ball slide on the ruler.
Or it just ejects? I think this is a very interesting question because if the ball slides on the ruler, you need to consider it's also the mu k.
We only measure the initial velocity rejected.
Yeah. So your initial velocity is defined by the ball leaving the ruler, right?
Yes.
So because I know that your camera might not be able to capture it, but do you include this sliding in your theory?
When it moves, we say it goes eject.
It's eject. So you assume that over the static friction point, it is ejected, and there is no mu k affecting on this ball. Is that what you mean?
Yes.
But can you prove that? Because that's just your guess. You cannot really show that there are not really. Okay. Can you prove that?
2 minutes.
Also, can I move to your setup?
Okay.
So in your setup, you use a spring.
Yeah.
And if we put the ruler in this direction, it's like this, right?
Yeah.
And your force is exerted on this
Yes.
plane, right?
Yes.
But in an ideal force, it is aligned and it should be like this.
So we capture the center of the area.
Is that because your ruler slides a lot? It slides a lot on your surface. So how can you say that it is always the middle?
1 minute.
We just
Like I see in your experimental setup problem, like the ruler slides a lot on like around here. Can you explain?
when the ball is still stable, or the ruler doesn't stop, doesn't slip.
Because I know that when you start to push more force, the spring starts to slide this way, right?
The spring.
Yeah, it starts to slide this way. I see that in your setup video.
Well, I'm sorry, the time has to stop here. Time has to stop here. The clock is setting, the setter is wrong. It should be ended at 10:37. So since you happen to be in a break, so that's stop right here, okay?
Okay.
So we have 1 minute preparation, or we switch to that.
So,
One more, sorry, you have 1 minute to propose to do the summary preparation.
oh,
All right. 没有. Oh, sorry. So you can could you restart the time clock? Could you restart the clock?
okay, so in our discussion, we discussed how the rotation of the ball affects the friction experiment. And they say that they use 2 bricks to prevent the ball from sliding, from rotating. And so I think that is a good idea. And they should add that in their setup to avoid some misconceptions. Also, we talked about the forces acting on this system. But in my opinion, the force from the strings change direction. So I think they need to consider this in their torque calculation. Also, we discussed about how the release point is defined in their system. And they just say that they keep the same point. Also, and they say that is the end point. But we failed to discuss about the polynomial fit. And I hope that they can explain it in my reporter's conclusion. Thank you.
So my first question is for the report. Did you consider the shape of the projectile? Because
The shape of it now?
Yes.
We don't use the ball.
you only use a ball. And then, do you think the shape of the projectile will matter? For example, if we use a cylinder instead of a sphere.
We don't, because we only use the ball. So because we only use the ball, also I can tell you the answer.
Okay. Then what about you? Do you think the shape will matter?
I think if this is the
If
ball,
it's the same height.
I think if this is the ball, I think they are the same. But in the experimental setup, conducting a precise experiment with the ball is more difficult.
Then on this image, we see that the spring is actually buckling, or it is not like in the entirely downward direction. And do you think this will matter? This question is for the report.
We think the angle of deviation to the matter.
Okay, so you think this is negligible, correct?
For the angle is too small, we think it is.
Okay. And for the opponent, you mentioned that there should also be a slipping phenomenon at the end of the projectile's motion. And how do you think this will affect its motion? Yeah, compared to the reporter's theory.
I think in their theory, they assume that the ball is at the very tip of the ruler. So
Yes.
after pressing down, the ruler completely leaves the ruler. But I don't think it's possible for that because that's just not realistic.
Okay, so you think the ball could also be in the middle of the set?
I think they should put it at the tip as much as possible, but I think there will still be motion, like effect of motion friction.
Okay. What do you think? What if we put the ball like not a bit offset off the edge, and there might be
There or there?
maybe about here?
Or here? I think it will change, but we don't do something experiment.
Okay. Going back to the projected page, the page where you did projected.
Well, time has to stop. Let's go preparation time for review 2 minutes. the reviewer, you can make your case if you like.
Okay, this is the problem statement. And first, I will talk about the pros and cons of the report. First, they have a clear grasp of the questions. They have a clear video setup. The stage definition is clear, and they use the Euler-Bernoulli equation to describe it. They also use error bar in their experiment. However, their energy conversion between the bending potential energy of the roller and the kinetic energy transfer is not clear, and they lack discussions of possible parameters such as the shape of the projectile. In addition, the opponent also mentioned that their experiment allows ball to roll, didn't allow the ball to roll, and they assume no roller curvature. Pros and cons of the opponent. While the opponent has a clear, organized presentation, they suggest use a machine instead of human hand to do the experiment, and I absolutely agree with that, because this way you can exert a stable force onto the roller. However, they did not consider the buckling of the spring. They consider that the buckling of the spring is negligible, which clearly is not the case, because we can see there is roughly a 15 to 30 degree angle in their experimental setup. And the first question and answer is, why did they use a polynomial fit to fit the data? And the reporter said they used the area derivation, but I am not really sure, because in their experimental in their experimental theory, they use a cantilever beam like the opponent mentioned, and this might not be the case in the bending roller. And the opponent asked if they did consider ball rotation in kinetic frictional setup, and the reporter said it doesn't really matter, and they use a box to mention it. But I think that both the box and their original set will not correctly measure it, and maybe you tying together several balls and then measuring their sum of normal forces can better determine the process, better determine the kinetic friction. The opponent also asked about the clarification symbol, and the reporter answered. And the opponent also asked about whether they considered the roller as a cantilever beam, but the reporter didn't give a clear answer. In the discussions, the opponent asked about the frictional coefficient, and the reporter answers they use a box to hold the position. However, like I mentioned before, even the box could accept the experimental setup. And the opponent also asked about what forces are at play here, and the reporter answered there are different directions of force due to the bending. However, both the opponent and the reporter think this can be neglected, but I don't think it can be neglected, as we can clearly see there is a buckling in the roller. Finally, they talked about whether the small angle can be neglected and be approximated using a linear-like relationship. Both the reporter and the opponent think yes, but no, I don't think so, because there is also bending, as we can see in the experimental video. They also talked about the ejection process, and the opponent said they should also consider kinetic friction. However, I think even rotational friction should also be considered. They also talked about the center of mass of roller. However, I don't think this is really relevant to the discussion, because the experimental setup didn't really mention that. However, in the setup video, the spring also experienced a force of gravity of the sum of the roller and marble, so I think that might also affect their forces applied. Thank you.
So the reporter, please take your final stand.
Okay, so this is our concluding remark. We derive our theory from the Euler-Bernoulli equation, like that, and we did experiment to prove that the theory is correct, and just the two equations. When we use the Euler-Bernoulli equations is that we consider the ruler is elastic, and we cannot just consider it as the rigid body, and we consider the rotation. And the measurement of friction, friction coefficient, we use little box to restrict the ball the rolling. And so it will flipping, not rolling. And the spring force direction shown about the first the swing direction of the spring force. We think the angle is too it shows not it shows not that we don't have to consider it, and the mu k should be considered. We think no, because we define the agent as a ball has the relative displacement, and the spring force should be the area should be circle, but we consider it as easy as the center. Thank you very much.
Well, so before finally finish his final remark, so now the time goes to the jurors here. Would anybody? Okay, Professor Bob, please.
I have a question for both of you. If you have a plastic ruler and another pair is a metal ruler, okay? So apply the same force such that the ball will eject. Which one will eject more efficient or more far further?
You mean to change the material, the cruise material. We think it is metal. For metal is more metal is more elastic as we observe.
How about the component?
I think what can eject farther is the ruler, because I think the ruler's static friction coefficient is higher, so you can store more bending energy in the ruler, and that actually leads to the higher ejection speed of the ball.
I think if we assume both the metal roller and the plastic roller to have the same frictional constant, maybe we modify the setting and we just base our experiment off the material, then the metal roller can bend more and store more elastic potential energy, so I think it will eject further.
Any other questions?
How do you measure the ejection force?
You mean how to measure the ejection velocity? We just use checker and catch the point, it start to move and eject and track the ball in several pages.
Pardon?
We use checker.
Check. Okay. So what's the relationship between the measurement and your formula?
The measurement.
You use C1, C2, C3 as a constant. Is that constant or not? Also with the function of alpha.
The function of alpha.
Yes, according to your source.
You mean this one?
Yes. What's the relationship between them? Is that correct?
We think for the algorithm theory, from the algorithm theory we derive the equations. So with three constant C1, 32, and 33. Okay, and we consider it as polynomial equation.
Why?
Just as our theory says, because the moment of error moment is because of the error moment.
Do you know which one is the bending, present the bending energy in this theory? Your Bernoulli bending theory. Do you know which term showing in this your Bernoulli bending theory? Which term represents the bending angle? Or the electric bending angle?
We consider the target. We consider target. The right hand.
Do you fully understand the meaning of this theory?
What?
Do you fully understand the Euler Bernoulli bending theory as you shown in the first equation in your slide?
Is that changing my knowledge?
I think since you can answer it right immediately, I don't think that we will have a good result. So let's stop right here. Okay. Now please go back to your seat, and the juror here will have to make the final judgment. Waiting for, we have one. One moment, please. So all the jurors are ready, I assume. So I will make the first one here. 5, 5, 4. Professor Han. 5 and 5. So now for the opponent, please. The opponent 6, 7, 6. One moment, please. Drummer, please. One moment. All in good times. Eight, 7. Okay, I will make the first one. 5, 7, and 7, and 8, and 6.
It's 7.
Oh, sorry, 7. Sorry, 7. So the Professor Han will have to make a change to 7. So, yeah. So if would any comment from the jury? Right? Or if that's okay.
Like, because I make very difficult and another for the reporter, my opinion is because from the question of the problem that you have to investigate the parameters, but I don't really could see clearly what term that you changing in this setup, and also the equations. So well explain.
Okay, any other comments from the juror? If there's no, then we conclude the fight, this game right now, this one. So, okay, let's move on. Now we have the break.